This one should be an interesting one. I had a viewer send me an RCA CC011, which is a Newvicon tube-based color video camera that RCA put their name on. It's actually a Panasonic-made camera. Yes, Panasonic made all the Newvicon tubes. And this was used as part of a two-piece portable unit that was out before the camcorder was invented. I got this unit. Let's tear it down and see what makes this thing tick. I had a viewer send me this old RCA color video camera. This one uses what's called a Newvicon color tube, and send it to me just so I can play around with this thing. We're going to tear this thing down. I mean, this thing isn't... I'll show you the picture of this thing. It's horrible. It's horrible. Let's take a look at the picture. As you can see, this thing has a god-awful picture. That's supposed to be red, by the way, that display. It is gross. I wonder what happens if I hit the white balance. There's a button on here that says white balance. I wonder what happens if I kind of point it at the lights and hit the white balance button. Is it going to correct? Is it going to make the color somewhat more usable? What these cameras had on them was they had a little white filter that went actually in between the lens and the pickup tube, so you didn't have to point them at a white card. You just pointed them towards a source of light, and they were supposed to auto white balance. And, well, it still looks like crap. Thing's got a viewfinder, a black and white viewfinder on here. And, I mean, these were really sad. If I hauled out one of my old Sonys with the, well, even the... I got a couple of old Sonys that one's got a Vidicon, what Sony call a Trinicon, and the other one's got the Satacon tube on it, Satacon mixed field. In fact, I've got two Sonys that use a Satacon tube. And those ones actually deliver pretty good color. This thing here is pretty sad. It came with a few accessories too. Let's take a look at what it came with. It came with this lens adapter. So what you did on this was you unplugged the lens and you unscrewed the lens. So that was the only good thing about these type of cameras with the C-mount lens. The Sony cameras did not have a C-mount lens, at least not the consumer ones. There's the pickup tube. As you can see, there's a filter switch here for indoor and outdoor. So outdoor, it just drops this filter in front, and when I put the white balance on, it does that. It just puts a white kind of opaque screen to try and give you kind of white balance. But it does have this adapter, and I don't know whether this is a wide angle adapter or a telephoto adapter. I guess we'll find out pretty quick. It's one of the two. It's either to make the image wider or make the image closer. But let's plug it in now and see. Oh, I think it's all gone green again. It's a telephoto, so it makes it... It's bad enough that the camera had to be back 20 feet before you could actually see anything with it, but now you got to be back 30. Because this just makes everything that much closer. It's got a black and white viewfinder here, a little black and white TV. And the circuitry is here, the tube is there. Be nice if that was a color viewfinder, but no such luck on this. This one's just black and white. But hey, that might be useful for something. No, it won't. As we'll find out when I open this thing up, this is unlike any other camera I've ever looked at. You'll see once we get into this thing. But this thing's got a pretty sad picture. It's all green. Let's take this off again. I have another lens. I should try the other lens I've got and see if it's any wider than this one, because this one here is... This lens is a 12 to 100 millimeter. Let's just see what the other lens that's sitting on my shelf is. Well, this one's a Canon lens. What was this one? Whose lens was this? Made in Japan. Feels pretty. Anyway, this is a Canon lens. This one's 11 to 70 millimeters.
So you can tell right off the bat that this is going to be a little wider angle.
Well, that is if it actually worked, but this lens came off a camera that had salt water in it, so guess what? The lens is FUBAR.
And it is. Arrows doesn't work on this one. I'm adjusting it and it's not closing. Yeah, for the early adopters of video, this is what we had to put up with, how bad the picture was on a lot of these cameras. I mean, the color on them was just horrible on a lot of them. Let's just try it. We'll try white balancing this thing here. I'll point it at a white card. What the heck, eh? See if I can get this thing to actually look sort of... There, that's a little bit better. Still looks atrocious. I think this lens is... This lens is no good. Let me go back to the original lens. So there's a look at my garage door. One thing these things were pretty cool doing though was video feedback was always kind of cool, and you got some pretty neat effects with these tube cameras. You know, like with the just the way that they bloom. You get the comet tail. Well, if you take a tube camera and you point it at a monitor, you can get some pretty wild effects. Video feedback, as they call it. And you know what? If you play with a laser, you can get even more cool effects. Enter the laser and video feedback. So by pointing the camera at the screen, and I've got a laser that's shining on the screen, you can get some pretty wild effects. Like pretty psychedelic. Now all you need to do is just record. You know, record the output of the camera. You got some pretty sick effects. We used to do this when I was, we did a video years ago when I was working for the community TV station. We actually did something like this. We did psychedelic music videos and stuff of local bands, and we would do stuff like this. We take one of these little lasers like this, point it at a monitor, point the camera at the monitor in a video feedback loop like this, and then just record it. And then we'd put the band in the studio with a blue screen and have them all performing and have this stuff in the background. It was wild. And you can do this with a tube camera. You don't get the same results out of a CCD camera, because the CCD camera, of course, doesn't have the lag the tube camera has, and that's, you really can get some neat effects. Of course, if I were to point the laser right into the lens, it would be bye-bye Vidicon tube. There is no second chance. If you do that, it's shot. If you point this thing at the sun, it's shot. And then, of course, while getting my feedback, if I rock the camera, then you can really get some cool effects by just turning the camera on its side, for example, or turning the camera upside down. Pretty wild stuff. Anyway, I promised a teardown video, so let's get tearing this thing down and see what's in it. So I'm just going to shut off the power to it. And we'll start taking this thing apart. Incidentally, this camera would have been of the era when Panasonic, I think, was making the RCA stuff. So this would be a Panasonic or a Matsushita camera, which makes sense because Newvicon was, of course, Panasonic. Hitachi had their Satacon. So any cameras that Hitachi made of this era would have had a Satacon tube in it, not a Newvicon or a Vidicon. Sony had their Trinicon, and the Trinicon tubes were a little bit different than the conventional color tube. And I'll try and get you guys some graphs here with my crude ability to draw. Oops. That didn't come off the way I expected it to. There's that cover off. Okay. Whether this thing goes back together or not, that's another story. But here's the inner workings of this. Got two big circuit boards here. We'll try and see which boards are which. So let me just undo the screws here. I want to flip these boards down so we can get a look. Now look at these boards, they're beautiful. The workmanship on this is just first rate. Look at the quality of the soldering on this. It's just beautiful. There you go. There's the Matsushita electric symbol. Not to be confused with Mitsubishi, because I had somebody that actually claimed that my little Panasonic TV had a Mitsubishi tube in it. No, 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 no. Mitsubishi is 3 diamonds that are touching. This one here is definitely a triangle with arrows on it. One more screw. There's one board out of the way. There's a wire that's cut off. I assume that went to the microphone, that it's no longer on this camera. You notice that this screw has a rubber washer, basically. These rubber washers, so does this one, these all have rubber washers on them. They're insulators, but what happens is the rubber itself will actually deteriorate and become conductive. We used to see that happen on these on devices that used a rubber washer like this to isolate. This side doesn't have it. This side's got rubber washer here because, as you can see, there are traces that go very close to where the screw hole is. So they have to insulate it, otherwise the screw would short it out. What would happen is these rubber washers would break down after a number of years and become conductive and cause all kinds of weird problems. So here's the two boards on here. Let's see if we can figure out which boards do what. This one's got a bunch of delay lines on it, so I imagine this one's probably the color board. And this one here is the high voltage generator and scan drive. Yes, and looks like the... Interesting. It almost looks as if the high voltage for this little CRT is actually generated inside the camera itself. It is. Look at this. I've never seen a design like this. It looks like the high voltage for the little CRT is generated back here. Let me get a wide shot here. So we have a high voltage line not only going into the picture tube or onto the camera pickup tube, but here there's another high voltage line which is going up to the viewfinder. Interesting. That is most interesting. You can see it. You can see it going right up through here. That's going into that viewfinder. So I bet you there's not much in the way of electronics in this viewfinder on this thing. Let's just take the top off it and see. Got to be another screw that holds this thing together. So I'm taking this off. It's got to be another screw in here somewhere. And I bet you it's under this. Of course, there is. Right there. Now this top should pop off to reveal nothing. Do not remove screws. Really, that's an invitation to me. Much better. Much better. See, this is why man invented the cordless screwdriver. For taking things apart. Okay, what else is holding this together? That's it. Oh, look, interesting. So, isn't this interesting? So you got your polarity reversal switch here for your left and right eye, and all the drive signals for this are generated on the main board. So in other words, what I'm going to find when I take apart this Viewfinder is not something that can be used for anything, because there's going to be no circuitry in here. There's going to be no drive circuitry whatsoever in this Viewfinder. It's all in the camera body itself. What else holds this together? Looks like it's just clipped together. It looks like this end piece might pop off. Right there's the picture tube. I just about broke it. So there is what's inside here. If I undo this screw, well, there's the Viewfinder. Real safe design, right? Send your high voltage right through the camera body, but this is the ultimate in being cheap. At least Sony and Hitachi had a separate Viewfinder that just plugged in and had all the self-contained circuitry for the Viewfinder. But as you can see, not this one. This one here has the little picture tube, and they've got all the high voltage wiring from that picture tube that goes back into the camera body itself, and everything is driven from the main board. So if someone wanted to change a Viewfinder on one of these, they'd have to actually unplug it, have to open up the camera, undo the harness. Like if you wanted to change the picture tube, for example, you'd have to find where it plugs in. In this case, there's 2 plugs here. Actually, I think there's 3 plugs. You have to undo the 3 plugs, pull the wiring harness back, undo the high voltage, and then there's one more plug up here. This, I guess, is probably for the, I'm thinking this is probably for the tally light. And then, and only then, you could remove the Viewfinder. Nice design, huh? But that also means that this little picture tube is not really useful for anything. I can't use it as a monitor for anything. I can't display an image on here because without the rest of the camera, it's not going to do anything. Although the little tube itself probably could be used, you know, powered up with another little TV. I'm sure that any of these little small TV circuits, little black and white TV circuit, would probably drive one of these tubes. It'd probably have too much high voltage on it, but you know, the tube itself could be driven with something else. But as far as
using it as a monitor, that's not going to happen. I guess it goes back together and goes onto this camera. But anyway, that's that part removed. Here's the tube. I want to tear this down even more than this. The chances are of this camera actually going back together are pretty slim. Of course, on reassembling it, I find that this ring that I had so much trouble taking off, well, the reason why is because it's screwed on. Not so bad to put it back together once you know that the ring was screwed on to begin with. Now I can put this viewfinder back on here and plug everything in, and then I can power the stupid camera up again. One of the reasons I'm plugging these back in is just because there's a good chance that if I try to fire the camera up without the viewfinder on there, that it's not going to turn on. Just because it's likely going to be looking for the CRT. It's going to be looking for the load, and without the little CRT here in place, there's a good chance that the camera itself just won't turn on. So that's one of the reasons I've reattached it here. Oh yeah, this plug's come out too. It won't work without that, that's for sure. That's the yoke for the actual Newvicon tube. There's the tube in the front here. It's not going to come out from the front very easy, is it? I'm going to have to take out this bracket, it looks like. But this is a little different. This one. There's another circuit board up top here as well. There's another board right up top, right there. I have no idea what that one does. I can just hear some old camera tech screaming now, "No, he's taking it apart wrong." Yes, I probably am, because I did not work on these type of cameras when I was in the business. I didn't work on any camera sections. I worked on camcorders on the recorder section, but I never actually did any work on the actual camera section itself, because in order to work on that you needed a light box to set them up, and it was about $10,000 I think at the time for the equipment needed to work on them. Okay, what is that? This looks like LEDs. Interesting. This thing looks like it's got, I mean, these look like LEDs in here. I wonder what happens if I power this thing up in this state. Make sure everything's plugged in. Of course, those LEDs are what's known as the bias light. I want to see something go boom. And it just may. Power switch is off. Okay, let's just see if anything lights up here. I hit the switch. Oh, look at that. I didn't expect that. It has two red LEDs that are shining on the back of the tube. Isn't that interesting? That is obviously it's biasing the tube somehow. I mean, I've seen the illumination of the actual, they flood the front of the tube with a bias light. I've seen that. I've never seen one where they've got, I think it's got 4 red LEDs that shine onto the neck of the tube. That is wild. Obviously it's biasing the tube somehow, but exactly what is it that they're doing? That is unique. That must be something that is unique to the actual Newvicon design. Basically what they do is they're using the glass as a light pipe to get the light up to the target, as opposed to having it right flooding onto the surface of the tube. I think that's what they're doing in this one. But this bloody thing's producing a picture. A bloody green picture, but it's producing a picture nevertheless, because the color balance is off by a mile. But this thing is working. That's incredible. Wish we get a shock working on this thing, poking around where the high voltage is. Yeah, right. Good plan. Okay, this is the LEDs. Looks like that goes to the little camera tube. So I wonder what happens to the picture if I unplug these things. Nothing, apparently. It still looks like crap. The effect is only apparent under low lighting conditions, which we'll show in a minute. Oh, it does change. Interesting. I'll shoot the screen. The picture changes when these bias lights come on. Okay, there's a shot of the screen that the camera is plugged into, as you can see. And I'll plug that little bias light thing in now. Watch the picture when I plug it in. See that? The picture changed. And I have a feeling it probably makes more of a difference in the low light. So if I turn the iris down on here to make the picture dark, because that's typically what the bias lights were for, was for when you were shooting in low illumination. So if I turn the iris right down so that we have a dim picture, now when I plug this bias light in, what is it going to do to the picture? It should clean up the noise. And you can see it when the lights come on and they go off. Off now. Now they're on. I think down in the shadows down here, the big difference is the lag. Watch the lag when they're off versus on. You see, notice that? It's subtle. I know I'm getting some noise on here because I've got shields and stuff off, but bias lights on, bias lights off. Sony used to flood the target with light. Red LED would just throw some light onto the target, and what that did was it kept a minimum amount of illumination on the target so that the target was always conducting slightly. You see, if there's no light at all hitting the target, so we cap the lens up, for example. And you've got no light. Ah, you see? Watch this. I'll put a lens cap on there. And I've got a lens cap here somewhere for this thing. I'll put my hand over it. Okay, so when the gain comes up, you can see all this noise. And I'm going to plug this bias light in and watch what happens to that noise. Whoa, look, it goes away. Or it goes down substantially. There's your noise. And it's in the green channel, of course, because the green makes up 60% of the value for the luminance. Plug the bias light in, the noise goes away. Let's study this phenomenon for a minute. Okay, the reason we use bias lights on the Vidicon, should say not Vidicon, we don't use them on Vidicons. We use them on Saticons, Plumicons, Newvicons, all these high sensitivity tubes. And on some, it'll just be shining on the faceplate. Like Sony, you just put an LED at the front, as I think I've shown in some of the Sony cameras I've taken apart. They just have the LED at the front, and it just floods the surface of the tube. This one here uses light pipes, so they've got the bias lights at the back, and they've got these two little plastic light pipes that run up the side of the tube. You can see the light pipes right here. I'll point them out with my screwdriver. Those are the light pipes, one on either side. And what they do is they carry the light from these LEDs up to the front of the tube. And I think that the light is probably also traveling along the glass. It's shining on the back neck of the tube, and it travels up the glass. So they're using the actual glass here as a light pipe to carry the light up to the front of the tube, or it will flood the faceplate. The question is, why do we need to do this? And the answer to that is it increases your sensitivity and it reduces lag. You see, what happens if this is your photosensitive surface, your target of the tube. So if we draw the front of the target, and the image is scanned like this on the inside of the target. So your scanning lines are going across, scanning like this. The target itself is charged up to a high voltage. So you've got a lead coming up here that's charging the target to a high voltage. And what happens here is as the scanning beam, so your cathode is in the back here and you're focusing electrons and stuff, focusing array and grid, and then your deflection coils are along the side here that deflect the beam back and forth and up and down. And as your beam is scanning across the surface of the tube from side to side, the image that's projected onto the target here, so if this is your image that you're drawing a little stick figure, your image that's on the surface of the tube, as the scanning beam scans across it, the surface of the tube is a photoconductor. It's like a resistor that changes its resistance with light that hits it. So where there's no light that hits it, the resistance is very high. And where the light hits it, the resistance is very low. So as the beam scans through the tube, it detects this resistance change from the light that hits the tube, and it causes a voltage drop on this lead here, which will have a high, very high mega ohm resistor feeding off to its power supply. B plus, we'll call it, for the tube. So B plus for the tube there, and then you have your video amplifier. I know, crude drawing for a transistor. It's going to be an FET too, but here's your video amplifier, and here's your video signal comes off of here. Okay, that's your video signal. As the tube is scanned, the voltage fluctuates on the target with respect to the light that's on that's onto the faceplate, that's focused by the lens of your subject. In dark situations where there's no light, the resistance is very high, and there's nothing to discharge the target because no light falling on it. So these electrons from the cathode are just bouncing around inside the back of the tube. Because there's nothing to discharge, there's no light or very little light falling on the target itself, you've got a buildup of electrons inside the tube which are bouncing around, and they're being picked up by the target, and some of them are going to leak through and they're going to get picked up by the video amplifier, and you're going to end up with noise. So by providing a light source, a bias light, to the surface of the tube, you are providing a minimum light level. You're keeping a constant bias on the tube, so even when the lens is capped up completely and there's no signal whatsoever, there's always going to be current flowing, because the amount of light that you are inducing as the bias light will keep that target from going into cutoff. It will keep the beam from cutting off. It'll keep the beam running at a minimum current at all times, even when there's no light entering the lens, or very, very little light entering the lens. And what it does is it reduces blooming, it reduces lag, which is we can do an experiment here. I can disconnect the bias light and we can see what lag looks like on this thing, and then I'll turn the bias light back on, and then maybe we'll do some other things like, I don't know, shine a flashlight onto the tube and see what it does to the picture. Because I guarantee you, if I shine a light on the back of this tube, I'm going to mess with the picture big time. You know, I try to play nice, and it would be nice to have a nice graphic here of a camera tube so that I have a little blurb that I'm going to talk about the different types of tubes here. I tried to get an image, that I found on the internet and tried to utilize it, but when I try to import the little image that I got off of Google Images and I try to bring it into my presentation, I get a big copy. This image is copyrighted and it won't let me import it. So screw them. I'll just print the goddamn thing and I'll take a picture of it with my digital camera and piss on them. So this is the image of, come on. I just want to use a graphic of a Vidicon tube. Come on, guys. Ridiculous, okay? But anyway, there it is. I just took a picture of it, complete with all the little dots that probably identify the serial number of my printer. All masked there in the background. We'll talk about the different types of tubes. There were a couple different types of tubes. First of all, there was the Vidicon tube. The Vidicon tube, the target that you see there on the left side of the screen, was a photoresistive target. And they didn't have much in the way of light sensitivity. So there was different types of tubes that were made, and I'm just going to read a little blurb here. The Vidicon tube was a video camera tube designed in which the target material is a photoconductor. The Vidicon was developed in the 1950s by RCA, or at RCA, by P.K. Weimer, S.V. Vorgu, and R.R. Goodrich as a simple alternative to the structurally and electrically complex image orthicon. This is from Wikipedia, just so that I don't get in trouble. While the initial photoconductor used was selenium, other targets include silicon diode arrays and have been used. The Vidicon tube is a storage type camera tube in which the charge density pattern is formed by the image-seen radiation on the photoconductive surface, which is then scanned by the beam of low-velocity electrons, as we've already explained. The fluctuating voltage is coupled to the video amplifier, is used to reproduce the scene being imaged. And the electrical charge produced by an image will remain on the faceplate until it is scanned, or until the charge dissipates. And some types of technology. Oh, and by the way, this construction was also on the Galileo probe to Jupiter in the late 70s, and NASA used Vidicons and all their deep space probes equipped with remote sensing. And, they've been around for a long time. Now, the Sadicon tube was developed in, I'm just looking to see when the other ones were developed. Yeah, Sadicon was the next one. The next most popular tube. That was developed by Hitachi, and it was a joint effort between Hitachi and NHK, which of course is the Japanese broadcaster. 1973, Thomson and Sony also produced them. And the big difference is the target. It's selenium with trace of arsenic and tellurinium added. So SEASTE to make it a little more stable. And the SAT is a derivative of the names of the three types of materials. And then we have the Newvicon tube. The Newvicon tube is Matsushita. 1974 was when the Newvicon tube was. Its light sensitivity or light sensitive surface is zinc selenide and zinc cadmium telluride. I can't pronounce this. Telluride, I guess. Yes, that's the Newvicon. Sony developed their own called the Trinicon, and we'll talk about the Trinicon because it's completely different than the others. So before we talk about the Trinicon, let's talk about the single tube color camera. On the single tube color camera, they overlaid the target or the photosensitive target with a color stripe filter, having a fine pattern of vertical stripes of green, cyan, and clear. So the clear passed all the colors. So you had green through the green filter, green plus blue through the cyan filter, and of course red, green, and blue through the clear. And what they did was the video level of the green component was always less than the cyan, and similarly to the cyan was always less than the white. So contributing or the contributing images could then be separated without any reference electrodes in the tube, which is how Sony did it with the Trinicon, which we'll talk about in a minute. If the three levels were the same, then that part of the scene was green. But the disadvantage of this was the light levels under the three filters were almost certain to be different, with the green filter passing not more than 1/3 of the available light. So that was one of the ways that they did it for the single tube, such as this camera. Now Sony, they had their Trinicon, and they had Trinicon Vidicon, and they had Trinicon Saticon. It doesn't matter, but they both work the same way. Sony used a vertically striped red, green, blue filter over the faceplate. It could be a standard Vidicon tube or a Saticon tube or any type. But so because they had the three colors, the red, green, and blue, what they ended up doing was they used a color stripe filter, but they also had to bury an extra electrode in the target that was detected by the scanning electron beam that was relative to the color stripe filter. So basically what that did was it worked like an indexitron CRT. As the electron scanned the surface, which would of course provide the red, green, and blue colors that were all multiplexed together coming out the video output, but there was an extra electrode that was buried in the surface of the tube, which actually had a wire coming off the front, and that went to the detection circuit to detect when the beam passed over that electrode. That was used as a reference for the timing signal so that the color circuits could then switch rapidly between red, green, blue, red, green, blue. They created an index signal. That was the beauty of the Trinicon single tube system. It delivers colors that were superior to other single tube and almost rivaled that of a 3-tube camera. Not quite, but they were very good, and they were used on a couple cameras. The DXC 1800 was one, the HVC 2800 was another, and it even made its way into the BV, I think it was, I'm looking here to see which one it was. It was a Betacam, a BVP1, which was the record-only cheap Betacam that was put out for basically the news gathering. They called it the disposable Betacam. Anyway, let's, you're tired of looking at this graphic. I'm tired of talking about it. Let's look at some experiments with this camera. So here's the picture in a relatively dark scene. I've got all the lights out here, so the only light that's in here is really coming from the monitor. The red bands you see, they're just interference because I've taken the shielding off of the tube itself. If I unplug the bias light without electrocuting myself, you can see the sensitivity increases on the tube, but watch what happens when I move. Ooh, look at the ghosting images there. That is what's called lag. You see all that nice, ugly lag that Vidicon tubes were really good at producing? Now, let me reconnect the bias light, and I bet you that lag will go down. So here comes the bias light back on, and, oh look, hello, the lag is reduced. The reason that the lag is reduced is because we are now flooding the surface of the tube with a little bit of light. We're keeping the beam from going into cutoff or getting too low. We're reducing the sensitivity of the tube for sure, because now we've got some dark current flowing, but we are increasing or decreasing our lag. I'll disconnect that bias light again, and now you can see, ooh, scary. Looks like crap. Now what happens if I take my fancy little flashlight here and we turn this on and we shine this on the back of the tube? Are we going to get the same effect? Now I'm shining a white light on it, not a red light. So what happens when I shine my flashlight on here? Are we still getting lag? Of course we are. If I turn my brightness up on my flashlight, okay, I've got enough light now that I'm going to reduce the lag. Yeah, you see that picture's flashing just because I've got boards disconnected and stuff here. But you see, there we go. There's a prime example. Laggy picture. Looks like crap. No laggy picture. And if I turn up the brightness, well, now I'm really killing the tube because I'm shining a bright light on it. So now I'm providing too much bias and we're getting all this noise because
the tube is now going into conduction, even though there's no light here. And the more I crank this thing up, the more it's going to mess with the picture. And now we don't have a picture at all because I'm shining so much light on the back of the tube here that the tube is going into full conduction. In fact, if I flick my white balance switch on this thing right now, it will probably try to white balance to my LED. I think that's the white balance switch I flicked. Could be wrong. Or was it this other switch? Of course, if I increase the light, lag is not going to be a problem, because it really only affects low light. If I shine my flashlight right into there, it's not going to like that, that's for sure. This is a bright light, as you can see. This is a really bright light. Okay, so that's a little demonstration of what the bias light is for. You see, you just learned something. And in case you guys are wondering where all this noise is coming from, well, if I just take my hand and move it near the, I'm just moving my hand near the actual pickup tube, actually to the wires going to the pickup tube, and I'm creating all this noise. It's because it's getting RF from my transmitters getting into this thing. That's what's causing all that noise, because I got the shielding off on this thing, right? So that's what's causing all that noise on the picture. I think maybe we'll look at some of these signals coming off this camera and take a look on the scope and see what they do. So I've put some of the shielding back on. You can still see the bias light through the side here. You can see it glowing red in the back of this tube. And I'm just going to, we're going to scope, take a look at some of these signals here on this board. There's test points here, so I want to take a look and see what signals we actually get off this board here. So, where did that come from? It's a piece of metal just lying there on the board. It must have been from the viewfinder when I took the viewfinder apart. Oh, look at that. When I switch, oh, you guys don't see that. Watch this. When I switch the left and right eye around, watch the screen. Halfway between left and right, there's no picture on the viewfinder at all, but we certainly have a blank screen here. So we'll clip on to one of the test points down here. Let's take a look at what we got on scope. Looks like we have a video signal. I'm at the vertical refresh rate right now. If I change my scanning rate here, I can look down at the sync level. This is vertical blanking. These are the individual horizontal lines that make up the picture. And if I continue to increase my scan duration, I'm just going to look at both sets here. So that's one field, field 1, and that's field 2, and this is field 1 and 2 to make up a full frame. But I can look right down at the individual sync pulses here, and then I can scroll across. There's my delay on the scope.
I really do need to read the manual to figure out all the features on the scope, because I get lost in the menus on this thing. It's so complex.
So if I pull,
this is probably one of the most advanced analog scopes that's on the market. What this thing can do is amazing in the analog domain. But it's easy to get trapped too and try to back your way out of something when you do something, and you got to try and figure out what you did to get back to scan an image again. It's almost embarrassing. I spent 15 minutes trying to get back where I was. Anyway, if you guys thought I was going to blow this thing up, tonight at least, I'm going to disappoint you, because I'm going to throw this thing back together as it is. And I think maybe at some point we'll plug this into a recorder and we'll do a video using vintage equipment. I can use my Sony, I've got a couple Sony cameras, and we'll play around with it and see what type of, well, how bad the pictures compare to everything else. We'll do a comparison of the different types of cameras, Newvicon, Satacon, Vidicon, CCD, and the likes. And I know I've done stuff like that before in the past using some different cameras. I've got a few more vintage cameras now that I can actually throw into the mix. So I think that's what we'll do, is I'll just throw this thing together, throw it back in the box, and say it was donated to me. And then we can play around with it and some of the other cameras at a future date, and just see what type of trouble we can get into. So that pretty much is it for this one for tonight. Thanks for watching. We'll catch you in the next one.